third example is going to have a triangular distributed load. So we've got our pin here at A, we have our roller here at B. I'm going to put my load from A to B. And it's going to have a maximum value of 15 newtons per meter. Then I'm going to add a point load out here of 150 newtons. Okay, from A to B is 9 meters. From B to my point load is 4 meters. And I'm going to put my coordinates at x1 here from A and x2 from the far right. And I wish to find the equations for the elastic curve. All right, so this one has my origins coming from two different directions. I'm only going to need 2 cuts because I only have what I call 2 changes. The first change is from A to B, my load stops and I have a roller, and then my second change is that load and the ending of the beam to the far right. So I'm going to need 2 sections. So I'm going to do my first section here 1, my second section here 2. Those are at arbitrary distances because x is going to represent a range. All right, solution. Now I did my math ahead of time, and I found that AY is going to be 44.167 newtons acting up at A. AX is equal to 0, and I don't care about B because both of my free body diagrams are going to be away from B. So coming here to free body diagram 1, I'm going to take to the left, and it represents 0 less than or equal to x1 less than or equal to 9 meters. It's going to have this portion of the beam with this distance, variable distance, x1, and I have my internal forces, shear 1, normal 1, moment 1, and I have my distributed load. Okay, now remember my distributed load ranges from 0 to 15. So if I'm looking at a range of distances, that means my load has to also be represented as an equation. So I'm just going to do y-intercept, so that's rise over run x, right, plus 0. Okay, so that's my height, or my y, right, because it starts at 0. And this is going to clean up a little bit to 5/3. Oh, good job. Let's put a line there. 5/3 x1. So that changes. Oh, and I can't forget my AY. AY is 44.167 newtons, and AX remains 0. So there's my free body diagram. So I'm going to go straight to my moment, summing moments about the cut or the section counterclockwise is added to the equation. I have 0 is equal to minus 44.167 times x1 plus my distributed load, so that's 1/2 base times height, and then the distance to its centroid from the section, so it's going to be 1/3 x1, because I do 1/3 from what I call the big end, so this right here is what I would call the big end, and then I have plus m1. So my moment 1 equation would be 44.167 x1 minus 5/18 of x1 cubed, and we are in a moment, so this is Newton meters. All right, slope times EI is equal to the integral of my moment. So that's going to equal 44.167x1 squared divided by 2 minus 5x1 to the 4th divided by 72 plus my constant of integration 1. And we've increased my x value, so that means we are now at Newton meters squared for the units on this side. And then vertical deviation, that's lowercase v for vertical deviation, is equal to the integral of the slope, which is equal to 44.167 x1 cubed divided by 2 times 3, which is 6, minus 5x1 to the 5th divided by 72 times 5, which is 360, plus c1 x1 plus c2. And again, that will be increasing that x value, which is a length value. So this is now Newton meters cubed. Okay, so there's my first slope and deflection equation. And then I'm going to take a free body diagram of section 2, and this one I'm taking to the right. So we're going to have 0 less than or equal to x2 less than or equal to 4 meters. And this free body diagram is going to be the little beam bit here with the 150 Newton load acting at a distance of x2. And we're going to have shear 2, normal 2, and moment 2. Now remember, we work in Newtonian physics, so equal and opposite signs. So if I'm doing a cut to the left, I've got down, out, and moment up. If I'm doing to the right, I've got up, out, and compression up. So that all my signs are equal and opposite in that section, and equilibrium is maintained. If I sum moments about the cut again, counterclockwise is added, I will have minus moment 2 minus 150 x2. So my moment 2 is equal to minus 150 x2, and again that's in Newton meters. So slope to EI is the integral equals m2 dx. I'm not putting my subscripts on everything here, which is equal to negative 150 x2 squared divided by 2 plus c3 Newton meters squared. And then my vertical deviation, lowercase v, EI, is equal to the integral of the slope, which is equal to negative 150 x2 cubed divided by 6 plus c3 x2 plus c4 Newton meters cubed. Okay, now I need to solve for those constants of integration, and I'm going to start with boundary conditions. Boundary conditions, I like to call those as where we know the answer. And we know that at the pen and the roller, vertical deviation is equal to 0. The pen is located at x1 is equal to 0, and the roller is located at x1 is equal to 9 meters, and at x2 is equal to 4 meters, because we have overlap at that roller. So we have 3 boundary conditions now, 3 different equations that we can solve for. So using at x1 is equal to 0, v1 is equal to 0, lowercase v for vertical deviation, I have 0 is equal to 44.167 times 0 cubed divided by 6 minus 5 times 0 to the 5th divided by 360 plus C1 times 0 plus C2. I realize that all these things are 0, and when you multiply by 0, it goes to 0, but I'm writing it out so you can compare it to the equation that I have written up here and see where all my values are coming from. And we find that C2 is equal to 0. And by the way, this is V1, this is X1, this is X1, this is X1, right? So now I'm going to do this again for the roller, which is at 9 meters. So at X1 is equal to 9 meters. V1 is equal to 0. Oop, I'm going to shift my equation down a little bit. So 0 is equal to 44.167 times 9 cubed divided by 6 minus 5 times 9 to the 5th divided by 360 plus C1 times 9 plus C2, which we just solved as 0. So there's that value now. And we will find that C1 is equal to negative 505.1295. I'm putting a lot of significant digits there because we're going to need that C1 value in another equation later on, because we have 4 unknowns and so far we only have 3 boundary conditions. Okay, last one is at X2 is equal to 4 meters. V2 is equal to 0. So that's going to be 0 is equal to negative 150 times 4 cubed divided by 6 plus C3 times 4 plus C4. All right, 2 unknowns, 1 equation. That doesn't do me any good. I am out of boundary conditions. We cannot have X2 go all the way over to 13 meters because it stops at 4 meters, right? That's the boundary that we set up for it here, okay? So we have to move to continuity conditions. Continuity conditions is where we have overlap. Now we already know we have overlap at the roller because deflection at the roller is equal to 0. That also means, ladies and gentlemen, that the slope over the roller has to be the same. So slope at X1 is equal to 9 meters and X2 is equal to 4 meters. So that's at the roller. Is the same, right? So that means theta 1 is equal to negative theta 2. Where's the negative coming from? Okay. When we have our normal coordinate system, right, we have X and we have Y, right? That's normally what we do. And so when we're in the first quadrant, counterclockwise is positive, okay? But now we're saying that X2 is going to the left. Vertical deviation is still positive up, which means that clockwise is now positive. So if we want the slope to be the same, it has to be the same magnitude and the same direction. So in order for that to happen, one of the signs has to change on one of my ordinate systems. If you're not first, you're last, so I'm changing sigma 2. So what this is saying is if I have a clockwise sigma 1, a counterclockwise sigma theta, this is a theta, a counterclockwise theta 1, then to make it a counterclockwise theta 2, I have to change the sign, okay? All right, so that equation is going to be 44.167 times 9 squared divided by 2 minus 5 times 9 to the 4th divided by 72 minus 505.1295, so that's C1, is equal to theta 2 negative 150 times 4 squared divided by 2 plus C3. Okay, so there's theta 1 at 9 meters and theta 2 at 4 meters. That's at the roller. And we will find that C3 is equal to negative 112.036. I'm leaving the units off because they get funky as we move on. So that means I can come in here and plug that value in up here. Negative 112.036. So that gives me C4 is equal to negative 371.991. All right, there's my 4 constants of integration using boundary conditions and continuity conditions, which means my answer, okay, I'm going to clean this all up. So for 0 less than or equal to x1 less than or equal to 9 meters, V1 EI, lowercase v, vertical deviation, is equal to 7.36 x1 cubed minus 0.0139 x1 to the 5th minus 505 x1, and you will be in Newton meters cubed. And then for 0 less than or equal to x2 less than or equal to 4 meters, little v2 EI is equal to, oh, I got my, okay, I wrote down some wrong values. So I'm going to come back here and correct this. Okay, C3 is negative 371.991. Negative 371.991, which means C4 is equal to positive 3,087.964. Okay, I'm sorry about that. So that means coming back here with that corrected error, I have minus 25x2 cubed minus 371. Let's do 372 because 3 significant digits is fine. X2, then plus 3,088 Newton meters cubed. Hopefully that's right this time.